Welcome to the Energy Absorber Capstone project, a protective hitch attachment for Class 3 towing hitches. Our team consists of Antonio Lucas, Darren Lim, Owen Ripes, Richard Sims, and William Lay. Starting off with the introduction, the Energy Absorber team was tasked with developing an energy-absorbing attachment for vehicles with Class 3 or 2" by 2" towing hitches. The attachment should minimize collision impact for both vehicles, reducing damage and occupant injuries. Additionally, we want the attachment to be highly customizable, allowing it to be used for a variety of customers and vehicle brands and increasing overall road safety. Next up, the problem statement. Nearly 30% of all accidents are rear-end collisions, mainly due to driver errors. Narrow metal towing hitches are attached to nearly 40% of road-going vehicles increasing, creating a safety hazard on top of the collision itself. The hitch can also translate damage directly to the vehicle frame itself, resulting in severe damage for even minor accidents. With an underdeveloped market for hitch protectors primarily revolving around smaller lighter vehicles, our goal is to produce a low-cost, lightweight attachment that reduces impact velocity from 30 miles per hour down to 10 miles per hour for even a 6,000-pound strut while maintaining desirable aesthetics. Moving on to the methods section. The function tree was established to segment the utility of the energy absorber into simpler parts to provide clarity for each step of the design process. The energy absorber procedure was broken down into 5 parts: system attachment, initial stage collision, medial stage collision, final stage collision, and finally decompression. Each stage is broken down respectively, intimately describing each procedure. Next, designing a purposeful product needs to be oriented to the customers. The categories and importance of customer requirements were established based on surveys and research. As the energy absorber's main function is to provide additional safety, the energy absorption category was rated with highest importance. This provides the team with a clear direction in mind when designing the energy absorber. The third stage of the designing process is to provide preliminary drafts of the energy absorber. Starting off with the concept selection, 6 designs were drafted by the team members who provided their version of the energy absorber. These designs were then rated in an evaluation matrix based on customer requirements. The strengths in each category in the respective designs were taken into consideration and therefore aided the creation of the final design. The next procedure is to test, validate, and improvise the final design.
Most of the math behind the energy absorber comes from machine design analysis, consisting of stress and strength calculations to decide on geometry and materials. We use energy calculations to determine how much energy we needed to absorb and the correlating impact velocity. Using a simplified MATLAB analysis, we modeled the system's worst-case scenario relationships between trucks to evaluate its effectiveness. Using SOLIDWORKS Evaluate, we tested our CAD models to make sure the system performed as expected, testing the load under a variety of conditions and circumstances, and redesigning the prototype to meet our goals.
Next up, the results.
The result is this: the energy absorber. A 5 feet by 9 inch by 15 inch composite bumper consisting of a damper for energy dissipation, an H-beam for structural rigidity, an aluminum shaft and connector for controlled buckling, aluminum honeycomb plates for deformation and energy absorption, a neoprene casing for impact resistance and environmental protection, and a plastic covering that comes in a variety of designs to match your vehicle. Here you can see the system makeup of the energy absorber, showing how each component aligns with each other. The shaft is pinned inside the receiver, and the damper is pinned and welded inside the shaft. The connector, H-beam, and honeycomb plates are welded together and surrounded by the neoprene casing, and finally the plastic cover. Here's an animation of the intended honeycomb plate deformation from above, and the honeycomb deformation from the front, showing it bulging outwards. And from the side, this time showing the deformation with a rigid wall backing. This is what it'll look like in the assembly. Here you can see the full assembly in motion, showing its deformation from the side with a force applied to the front. You can also see the beginning of buckling of the shaft. Here's the same animation from the top, clearly showing the controlled buckling and protection of the hitch receiver as it does not deform. In a low-speed collision, the energy absorber will elastically return to its natural state. Here you can see a mock crash. Should the energy absorber perform as intended, the impacting vehicle will come to a complete stop with an elongated collision. Here's the simulated collision from the side. As you can see, there will still be space between the two vehicles even after plastic deformation of the energy absorber. As it currently stands, the energy absorber has a critical force resistance of 6 kilonewtons, corresponding to a repeatable crashing speed of 3 miles per hour. This means that below 3 miles per hour, the system will rigidly protect both vehicles from damage without plastic deformation. Between 3 miles per hour and 10 miles per hour, the damper and honeycomb will act in unison to absorb the collision impact and reduce the system's energy. At 85 kilonewtons of impact force, or a crashing speed of 10.6 miles per hour, the shaft will begin to buckle, signaling total system failure. Thus, the energy absorber reduces vehicle collision speed by 10 miles per hour, below the intended goal.
Finally, the conclusion. To summarize, the team has managed to design and validate the energy absorber system. It started off with defining key requirements to aid the team with the designing process. Through careful selection, the final design was curated and was put through the rigorous simulation, which tested the static, dynamic, and fatigue analysis of the system. Simulation has proven that the energy absorber is a reusable device in minor accidents and is also effective at substantially mitigating impact on colliding vehicle at higher speeds. To ensure marketability, the product was designed to attract a wide group of consumers through the ability to customize. Finally, a 25% scale model was produced to provide a visual representation.
Future steps include testing a 12-inch damper alternative that, according to our calculations, will provide the necessary energy dissipation to reach the 20 miles per hour reduction goal. This will require a custom damper, which we can combine with physical prototyping and crash testing to finalize our analysis. Once our final iteration is complete, we'll demonstrate the energy absorber at auto shows and social events like the Atlanta International Auto Show, or SEMA, and there may even be potential cooperation with automakers to provide the energy absorber with vehicles as standard. But that's all we have for now. Thank you.